Welcome to College Algebra for STEM majors. This course is designed for people planning to take calculus. We begin with R.1, which is a review section about the real number system and sets. Let's just talk about the real number system quickly. This is the number system that you are mostly familiar with. It's called the real number system. And this number system began with a very simple set of numbers called the natural numbers, or sometimes the counting numbers. And this is nothing more than the set of numbers 1, 2, 3, 4, 5, etc. In other words, the numbers that we use for counting. Eventually, it was known that we needed a number to represent nothing, and so we add the number 0 into this set of numbers. When you add the number 0 with the set of the natural numbers, you get what's called the set of whole numbers. It's a very small but important addition. And then eventually we needed the concept of negative numbers. So when you throw in the opposites of all of these counting numbers, you get what's called the set of integers. Now, the next step in the evolution of numbers is the set of rational numbers. So if you think about a loaf of bread can be cut into pieces and a unit of time or money can be subdivided, rational numbers are represented by the division of two integers, r divided by s. Now, when you divide two numbers, you don't always get a whole number, so that's why this creates a new set of numbers. And the rational numbers are numbers like 1 divided by 3 or negative 1 divided by 4, etc. And I want you to notice that when you divide two integers, you either get a terminating decimal or you get a repeating decimal. You get one or the other. Even numbers like mixed numbers like 4 and 2/5 is a rational number because it is the same as 22 divided by 5. And if you really wanted to, you could convert that into a decimal. 22 divided by 5 would be 4.4. And then finally, we get the set of irrational numbers. And irrational numbers are numbers that are not any of the numbers that we just mentioned. So they're not whole numbers or integers or rational numbers, but they are nonetheless very important numbers. Numbers such as the square root of 2 or numbers like pi, these are irrational numbers. Now, what makes them irrational when you take a number like the square root of 2? The decimal approximation of the square root of 2 is an infinite but non-repeating decimal. And the same thing with pi. If you look at the decimal expansion of pi, it's 3.1415926, etc. Well, this is an infinite, non-repeating decimal. The real number system consists of all rational numbers combined with all irrational numbers. So the real numbers is all rational and irrational numbers. Combined. Now we move on to properties of real numbers. And these will mostly be reviewed, but we want to make sure that we state them for the record. The associative property has to do with how we group numbers when we are adding or multiplying 3 or more numbers. So for example, if we are adding the numbers A, B, and C, it doesn't matter if we add B and C first and then add A, or if we add A and B first and then add C. The same thing is true for multiplication. It does not matter the order in which we multiply 3 numbers together. The commutative property basically just says that it doesn't matter the order in which you add or multiply 2 numbers. So if I just have 2 numbers, A and B, it doesn't matter if I say A plus B or if I say B plus A. And the same thing for multiplication. A times B is the same as B times A. Next, we have a few additional properties. First is the distributive property. A times B plus A times C is the same as A times the quantity B plus C, where A, B, and C are any real numbers. Also, we have the additive and multiplicative identities. The additive identity is the number 0. The multiplicative identity is the number 1. And the reason they are called the additive and multiplicative identities is because 0 is the number that we can add to a number A to still get A, and 1 is the number that we can multiply to the number A to still get A. Finally, we have the additive and multiplicative inverses. The additive inverse of a number A is denoted negative A, and sometimes we call that the opposite of A. And the significance here is A plus negative A is 0. The multiplicative inverse of a real number A, which is also called the reciprocal of A, is 1 over A, as long as A is not 0. And the reason for this is that A times 1 over A is equal to 1. So when you add the additive inverse to a number, you get the additive identity. And when you multiply the multiplicative inverse to a number, you get the multiplicative identity. And again, these are all properties that I think we know, but it's good to state them just so that we have them for reference. In our first example, we are asked to simply identify what property tells us that each of the following are true. So in the first problem here, we have 4 plus 6 is equal to 6 plus 4. So we're adding the same two numbers, but we are switching the order. This is the commutative property. Now, technically, it is the commutative property of addition, because addition is the operation here. But mostly, I just want you to know that this is the commutative property, which says that you can switch the order in which you are adding a couple of numbers. In the next example, we have 3 multiplied by 5 minus 8 is the same as 3 times 5 minus 3 times 8. So what's happening here is the 3 on the outside is being multiplied to 5, and the 3 on the outside is being multiplied to 8. And when you do this, this is the distributive property. And the way I like to think of it is that we are distributing the 3 to each of the 5 and the 8. So we are multiplying 3 to 5 and multiplying 3 to 8. Next, we have 2 times the quantity 3 times 5 is the same as 2 times 3 multiplied by 5. So notice that we have the same numbers, 2, 3, and 5, being multiplied in each one of these. But one time we are multiplying the 3 and 5 first, the other time we're multiplying the 2 and the 3 first. So basically, we're just regrouping. We're reordering which ones we're multiplying first. When you do that, this is the associative property. So the associative property has to do with changing the grouping. And finally, here we have 4 times 1 is equal to 4. So we're saying that when you take the number 4 and you multiply it by 1, you are getting the same number 4. So the number you're starting with identifies with the number that we end up with. So this is the identity property for multiplication, right? Because 1 is the multiplicative inverse, or 1 is the multiplicative identity, rather. So this is the multiplicative identity property, and of course for multiplication. Now, I'm not going to test you on, knowing the properties, but what I want you to know is when we're having conversations about these things and I say certain words like commutative, associative, distributive, you should know what we're talking about. So we want to have a working knowledge of what these words mean. Next, we're going to talk about sets and intervals. So in mathematics, a set is simply a collection of objects. And each object in that collection is called an element of the set. And sets are often denoted by using a capital letter, like capital A, for example, and written using these braces to enclose the list of elements, and then we separate them by a comma. So for instance, the set A, consisting of all whole numbers less than 6, can be expressed as A equals the numbers 0, 1, 2, 3, 4, and 5. A set with no elements is called the empty set and is denoted one of two ways. You can either write the braces with nothing inside, or you can use the empty set notation, which is kind of like a 0 with a slash through it. If A and B are two sets, then their union, which is denoted A union B, is the set of all elements in A or in B or in both. The intersection of set A and set B is denoted A intersect B. Notice that the intersection sign is just the upside down U. And this consists of the set of elements common to both A and B. So let's just do a couple of simple examples here. So in the first one, we are asked to find the set B union C. So union means you're going to take the two sets and put them together. So set B is the set consisting of those 5 numbers, and set C is the set consisting of those 4 numbers. So B union C is going to be the set containing all of the elements of B along with all of the elements of C. So I'm going to first just simply list all of the elements of B, which are these elements here, and then I'm going to list all of the elements of C that I have not already listed in B. So I want you to notice that the first element in C is -3, but we already have that listed here, so there's no need to list it again. Then we have 0, and notice that 0 is not listed, so we'll add that to our list. And then we have the number 2, which is also not listed in set B. And finally, we have the number 7 here, and 7 is already listed in B. You can see it right here, so we don't need to list it again. So the set B union C is a set consisting of the numbers -3, -2, 4, 7, 9, 0, and 2. For the second example, we're asked to find A intersected with B. Now, to do the intersection, we're going to look at the set A, which is this set here, and the set B, which is this set here. And the intersection of the two sets is the set of the things they have in common. So what numbers are in both sets? Well, notice that -2 is in both sets. Notice that +4 is in both sets. And that is it, right? The number -1, 1, and 5 all belong to A. And the numbers -3, 7, and 9 all belong to B. But none of those numbers are contained in both sets. So the intersection of A and B is -2 and 4. And finally, we have the intersection of A and C. So this is the same idea, except now we are going to look at set A and set C. And again, we are going to list all of the elements that they have in common. Now, if you look carefully, you'll notice that none of the elements of A are also in C. And vice versa, of course, is also true. None of the elements in C are in A. So they have no elements in common. So their intersection is going to be the empty set. And I don't really like this notation. I like to put the 0 with the slash through it, okay? So that just indicates that they have no elements in common. Next, we're going to talk about set notation versus interval notation, and then also the graph. And again, all these things should be review, I hope. So in the set notation, let's look at the example where we talk about the set of x such that x is a number in between a and b. So x is less than or equal to b, and x is greater than or equal to a. In interval notation, we write that in the following way, and we'll come back to this. But let's go talk about the graph. So when we say x is a number in between a and b, we're saying on a number line, we're looking at all the numbers x that are in between the number a and the number b, and because we have equal signs on both of these, we're including both of these points, right? So this is what the graph is. Once you understand the graph, the interval is pretty easy to get. All we're looking at is all the numbers from a to b and all the numbers in between. So the way we write that is a comma b, and then we put brackets here to indicate that these numbers are included. Okay, now a slight variation of that is, what if the equal signs are not there? So we're still looking at x as a number that is bigger than a but smaller than b, but now we're not including the left endpoint and the right endpoint. So on the number line, what this looks like is we put an open circle on a and an open circle on b to indicate that it is not included. And the way we make a distinction between this set of numbers and this set of numbers is when we do not include the endpoints, we use a parentheses instead. Now, the next couple of examples are essentially the same thing, but notice in one we are including a but not b. In the other, we are not including a, but we are including b, and you can see that on the number line here. The solid dot means we're including, the open circle means we are not including, and then where you have the solid dot, you will have a bracket, and where you have the open circle, you will have a parentheses. Now, you can get into some open-ended intervals. So if we say x is greater than or equal to a, what that means on the number line is we're going to have all the numbers x that are larger than a. So that would be all the numbers to the right of a. And in this case, including a as well. So again, that's why we have the bracket, and that's why we have the solid dot. If a is not included, we change that bracket to a parentheses. We change it to an open circle. And then, of course, we can also talk about x is less than a. That just means we want all the numbers to the left of a. And again, we can look at whether it's included or not included, etc. And finally, we get down to the last set, which is the set of all real numbers, which means all numbers from negative infinity to positive infinity. And the graph for that, of course, is just going to be shading everything. Let's do a couple of examples. So in the first example, we are given the interval notation, and we want to use the set notation. So to do this, the first thing I'm going to do with my interval notation is I'm going to draw this on a number line. So here we have a number line. The two important numbers are -2 and +3. And this interval says we want all the numbers in between -2 and +3. And actually at 3, we have a bracket. So let me change that to a bracket. So when we go to graph it, we want all the numbers in between here, just like this. At -2, we are not including, so we put an open circle. But at +3, we are including, and we put a solid circle. And so in set notation, we would write this as the set of all x such that x is in between -2 and +3. So x has to be less than or equal to 3, and x has to be greater than -2. For the second one, we have the interval notation, -infinity up to 4. First, I'm going to graph that. Now, when you graph this, there's really only one important number, and that is the number 4. And this set of numbers says that we're coming from -infinity, which is somewhere over here, and we're going all the way up to 4, and we stop at 4. And 4 is included because it has a bracket, so we put a solid dot there. So now in set builder notation, this will be the set of x such that, how do we describe this? Well, these are all the numbers x that are less than or equal to 4. So we're going to say x is less than or equal to 4. In the next example, we're just doing the opposite. Now we have a graph, and we want to write the interval graphed here in interval notation. And to me, this is a little bit easier. So we're looking at all the numbers graphed here, which are all the numbers starting at -3, up to, and stopping at +2. So when I go to create the interval there, I'm just going to write the number -3 up to, comma, 2. Notice that -3 has a solid dot there, so that means it's included, and +2 has an open circle. That means it is not included. And so this would be the interval notation for that graph. The next example is a little bit more complicated. It says to find the indicated set and graph. And actually, what I'm going to do is kind of the reverse of that. I'm going to look at the graph first and then use that to get the indicated set. So in part A here, we have the first set here is all the numbers in between +1 and +4. So on the number line, here's +1, here's +4. We have all the numbers in between there, so I'm going to graph that. But when I graph it, I'm not going to put it on the number line. I'm going to graph it above the number line. So all the numbers in between 1 and 4 are all these numbers up here, and we are not including 1, and we are not including 4. Again, that's because we have the parentheses there. And we are going to put this together with the interval from 2 to 5. So what does this look like on the number line? Well, 2 is right about here, and 5 is here. And we're going to do the same thing. We're going to graph all the numbers in between 2 and 5. So here's 2 up to 5. And this time we are including the 2 and we are including the 5. So we're going to put a solid dot there and a solid dot there. Now, on this number line, I'm going to graph what we're trying to get here, which is the union of these two sets. Now, union means we are putting these two sets together. So every number that belongs to one set or the other set is going to be a part of our final answer here. So we do not include the number 1 because it is not included here, but we do include all the numbers in between 1 and 2. We include all the numbers in between 2 and 4. And we also include all the numbers in between 4 and 5. And finally, we do include 5 because it is included here. And so in interval notation, this is the set of all numbers beginning at 1, stopping at 5, including 5, but not including 1. In part B, we have the same two set of numbers, but now we are looking at the intersection of those sets. So I'm going to once again graph each one of these, and the graphing will be quick because it is the same two sets of numbers. So the set of numbers between 1 and 4 is going to be this set of numbers, and then the set of numbers from 2 to 5 is this set of numbers. And then when you're talking about the intersection, right, that's what this symbol means, the intersection, what we need to do now is only graph the numbers that both sets have in common. So we are going to graph all the numbers in between 2 and 4 because these numbers belong to both sets. We will include the number 2 and we will not include the number 4. Right? Now, the reason we include the number 2 is because 2 is included here and 2 is included here. But we do not include 4 because even though 4 is included here, 4 is not included here. and it has to be in both sets to be included in your final answer. So our final answer here for this one is all the numbers from 2 to 4, including 2, not including 4. Next, we talk about the concept of absolute value. The distance from the origin on a number line to a real number c is defined as the absolute value of c. And the way we denote that is with this notation right here, with the vertical bars. The absolute value of a number is always non-negative and is also known as its magnitude. Now, the technical definition for the absolute value of x is that it's equal to x if x is already greater than or equal to 0, and it's equal to negative x if x is less than 0. Now, before we do these examples here, let me just say a little bit more about this definition. So if I have a number line here, the origin of the number line just refers to the number 0. And if I have a number over here like negative 4, the absolute value of the number negative 4 is nothing more than the distance that negative 4 is away from 0. And that distance, of course, is 4 units. So we would say the absolute value of negative 4 is equal to 4. Likewise, if I have a number like positive 3, the absolute value of positive 3 is once again just referring to the distance that the number 3 is away from 0. And that distance is equal to 3. So the absolute value of 3 is 3. So it's a relatively simple concept. So what happens with this definition is sometimes students get a little bit confused because they wonder, why do we need this complexity? Well, here's what it basically says. The absolute value of x is x if x is positive or 0. So in other words, if x is a positive number or if x is already just equal to 0, then the absolute value of x is just itself. But the absolute value of x is negative x if x is negative. Now, why is that? Well, because when you have a negative number, the distance that that negative number is from 0 is always going to be the opposite of that negative number. And that's because distance can't be negative, right? So when I say something like, what is the absolute value of negative 4? The definition is you have to take the opposite of x. So you have to take the opposite of negative 4, which gives us positive 4. Okay, so that's the reason that we need this technical definition for the absolute value. Now, when you actually go to do computations, I don't expect you to use the technical definition. I would expect everyone to know the absolute value of negative 4 is simply 4 without showing any additional work. Okay, let's go ahead and work these examples now. So in the first example, we have the absolute value of negative 3. Well, this is just going to be equal to 3, right? Not much to explain there, I don't think. And the second one, we have negative 4 minus, and then the absolute value of 4.5. So you need to work out the absolute value first. So this is negative 4 minus, and then the absolute value of 4.5 is 4.5. So we have negative 4 minus 4.5. This is negative 8.5. And finally, in the third one, we have the absolute value of negative 4 plus 9, and then plus 3. So we're going to talk about order of operation next, but basically what you need to do here is you need to work this out first. So negative 4 plus 9 is 5. So this becomes the absolute value of 5 plus 3. Well, the absolute value of 5 is 5 plus 3, and 5 plus 3 is 8. Next, we'll look at a couple of properties of absolute values. First of all, the absolute value of any number a is always greater than or equal to 0. That just means the absolute value of a number can never be negative. The second property, the absolute value of negative a and the absolute value of positive a are the same. Third property, if you have the absolute value of a times b, you can do that by taking the absolute value of a and multiplying it by the absolute value of b. And finally, the absolute value of a divided by b is the same as the absolute value of a divided by the absolute value of b, as long as b is not 0. And then we have, for the last property here with absolute values, is that if a and b are 2 points on the number line, so in other words, if a and b are two numbers, the distance between a and b is given by either the absolute value of b minus a or the absolute value of a minus b. It doesn't matter which one you use. So a quick example of that, let's suppose that I'm looking at the numbers -4 and +5 on the number line. If I want the distance between -4 and +5, I can calculate this by taking the absolute value of -4 minus 5, or I can calculate it by taking the absolute value of 5 minus -4. And I want you to notice that you get the same answer for each. So if I do it the first way, I have the absolute value of -4 minus 5, which is -9. And we know the absolute value of -9 is +9. And if I do it the second way, 5 minus -4 is the same as 5 plus 4. And 5 plus 4 is 9. And the absolute value of 9 is 9. And this should make sense because if you look at a number line, -4 is over here, +5 is over here, and 0 is in the middle, the distance between those two numbers is pretty clearly 9 units, right? We know it's 4 units here and 5 units here, and 4 plus 5 is 9. So to find the distance between two numbers, you just take the absolute value and you subtract the two numbers. And the order that you subtract them really doesn't make any difference. Next, we talk about order of operations, otherwise known as PEMDAS. So when evaluating a mathematical expression, we need to know what thing to do first, what to do next, etc. So we're going to perform the operations in the following order, beginning with the innermost parentheses and working outward. So you always start with parentheses, that's what the P stands for. Then we are going to simplify all numbers with exponents, so that's the E. Then we perform all multiplication and division, working from left to right, so that is the M and the D. And finally, we perform addition and subtraction, working from left to right, and that is the A and S. So this acronym, PEMDAS, helps you remember what to do first, second, third, etc. Let's take a look at these examples. So in the first problem, we have 3 squared plus 2 times the quantity -3 plus 7. So you always start with working your parentheses. So we need to work the inside of these parentheses. Now inside, we simply have -3 plus 7. So when we perform that, we just get 4, right? -3 plus 7 is 4. Now we have basically taken care of these parentheses. So next up, what we have is an exponent here, and then we have multiplication here. So we're supposed to do the exponent and then the multiplication. Now technically you can do those at the same time because they are separate from each other, but we'll be very careful in this first go around. So 3 squared is 9, and then we have plus 2 times 4. Now between addition and multiplication, you do multiplication next. So 2 times 4 is 8. This is 9 plus 8. And 9 plus 8 is 17. In the second problem, it's a little bit special. We have 3 squared plus 1, and then over 4 minus 7. When you have a fraction, you kind of treat it like two problems. You need to work out the numerator and the denominator separately from each other. And then the last thing you will do is the actual fraction itself, which means division. So in the numerator, we have 3 squared plus 1. So we're going to do the exponent before we add. So 3 squared is 9. So that's 9 plus 1. In the denominator, we have 4 take away 7, and 4 take away 7 is negative 3. So not a whole lot to do there. And then now back to the numerator, 9 plus 1 is 10, so we have 10 divided by negative 3. And because this doesn't divide evenly, I'm just going to rewrite this as negative 10/3. Now, if you divide that on a calculator, you'll get negative 3.3333, but we'll just leave it in the form negative 10/3. And in our last example here, we have a little bit more complicated expression. So we just got to be careful. And the main thing is just don't go too fast. So first thing I'm doing here is I'm just going to rewrite the problem. You have to really try to avoid making common mistakes. So I will see a number of students who will say 6 plus 3 is 9, right? And they'll just want to do that first to take care of it. But the way order of operation works is you are supposed to start with the innermost parentheses first. So we are starting here, and we're going to work whatever's inside there. So negative 3 squared, this actually means negative 3 times 3, right? So that's negative 9. So everything else stays the same, 6 plus 3 times the quantity 5 minus, and then we have negative 9 plus 2. So all I did there was the exponent inside of the innermost parentheses. Now, I still need to do negative 9 plus 2, which is negative 7. So again, everything else stays the same. And now, this set of parentheses is done. So now I move to the next set of parentheses, which is telling me to now do 5 take away negative 7. Well, remember, 5 take away negative 7 is the same as 5 plus 7, and 5 plus 7 is 12. So this number just becomes 12. So we have 6 plus 3 times 12. And now we're down to 2 operations. We have addition and we have multiplication. Multiplication comes first. So this is 6 plus 3 times 12 is 36, and 6 plus 36 is 42. Just a couple more examples of order of operation, and this time they tell you that you can check your output on a calculator if you want. Some calculators will handle this just fine. Other calculators will sometimes be incorrect depending on how you type it in. So in the first one here, we have 4 plus 10 divided by 5 plus 2. There are 3 operations. You have addition, division, and addition. Remember that if you have addition and division, division comes first. So we should be doing 10 divided by 5 first. So this is 4 plus 10 divided by 5 is 2, and then plus another 2. And now we just have addition, and we can just do that in order. 4 plus 2 is 6, and 6 plus 2 is 8. In the next one, we have 4 plus 10 over 5 plus 2. And as we mentioned on the previous page, you need to do the top first and then the bottom second. So 4 plus 10 is 14, 5 plus 2 is 7, and then 14 divided by 7 is 2. Now, what will happen on a calculator if you try to do this? If you just type in 4 plus 10 divided by 5 plus 2, this will be incorrect on a calculator, because what the calculator will do is it will do 10 divided by 5 first, just like we did in the first example right here. And so that'll work out as 4 plus 2 plus 2, which we know is 8. So if you're doing this on a calculator, you need to tell the calculator, do this first, do this second, and then do the division. And the way you do that is by using parentheses. So on a calculator, you would need to say 4 plus 10 in parentheses, that's the numerator, divided by 5 plus 2 in parentheses, that's the denominator. And the calculator will see this as 14 divided by 7, which would be the correct answer, which is 2. So when you're using a calculator to do some of these things, particularly when you have fractions, you need to make sure you put parentheses around the numerator and the denominator of the fraction.